Okay, the next thing we'd like to talk about are birefringent materials. A little bit complicated. You'll see how it works. A birefringent material is used to make a half-wave plate, which is the other optical component we need to discuss. All right, bear with me for a second while we go through this. There we are. Birefringent materials are usually crystals, and they have the property that the index of refraction in one direction, or for light polarized in one direction, will be different than the index of refraction for light polarized in other directions. That may seem very odd, but it's not that unusual in a crystal. Maybe the atoms stack up in such a way that the density of that the type of electronic bonds that are oriented in the vertical direction look different than the atomic bonds that are oriented in the two orthogonal directions. In that case, it's very natural that the index of refractions would be different. In fact, birefringence is very common. Even crystalline quartz is birefringent, and so are many other familiar materials. Okay, let's see what happens when light crosses one of these materials. Okay, so here I have a crystal that we'll assume to be birefringent with one index of refraction, Ne, for light polarized in the vertical direction, and another index of refraction, N0, for light polarized in the other two directions. Okay, and these two numbers are different. Suppose we have light polarized in the vertical direction and it crosses this material. Let's contrast that with what happens when light polarized in the perpendicular direction crosses the material. And what I want to show you is that when they emerge, even if they were in phase in the beginning, they'll emerge with a phase shift. Okay? Let's see why that is. Okay? Well, to begin with, examine the time to cross the material. Of course, it's different because the waves move at different speeds since the indices of refractions are different for the two beams of light. So the time to cross for the vertical component, which will just be the distance it has to travel divided by the speed for the vertical component, will be the following. It'll be the distance divided by, and remember, it will be the speed of light in vacuum divided by the index of refraction. So C divided by NE. Or we can write this as NED over C. In contrast, for the horizontal component, the result will be very similar, only the index of refraction is different, and 0D over C. So they won't be equal, okay? Because the time to cross isn't equal, there'll be a phase shift between them. How much? Well, if the light were delayed by one whole period, that would be 2 pi radians. So in general, the phase shift will be epsilon, will be 2 pi radians times the actual time difference divided by 1 period of oscillation, or 2 pi times the time difference, TV minus TH, divided by capital T, or equivalently, times F, where F is the ordinary frequency. Okay? Actually, it's convenient to write this in terms of the wavelength. Remember that the frequency is C divided by lambda, then this is 2 pi divided by lambda times TV minus TH, and the C's cancel out. Okay? Oh, no, not yet though. Excuse me, times C. Getting ahead of myself there. Finally, let's put in these times. And then we have 2 pi over lambda. Well, TV is NE times D over C, and TH is NO times D over C, and then we have to multiply all this by C. Now the C's cancel out. And we have finally 2 pi times D times NE minus N0 divided by lambda. Very good. We could write this in other ways, but this is actually convenient for what we want to do. Okay? Let's stop there. I'm just going to put a box around this for so that we remember it. And then in a second, we'll go on. Of course, the reason that this is important is this shows us that we can use a birefringent material to control the phase difference between vertical and horizontal components of a light wave. If we can control that phase, we can do things like turn linearly polarized light into circularly polarized light. Or we could turn light of one polarization into light of an orthogonal polarization, as you'll see in a moment. By the way, those are the jobs of two types of optics, a quarter wave plate and a half wave plate. And we're most interested in the second one, the half wave plate. We'll take a look at that in a moment, okay? Before that, I'll just have you do an example where you put in some numbers for a typical birefringent and for a typical wavelength of light and see what sort of phase shifts you get. Okay, see you in a moment.